So, hello everybody, whoever is here. So today I'm happy to host Kaplun from Harvard that will speak about understanding generalization requires rethinking deep learning. So, Gal.
Thanks a lot for the introduction. So I'm going to talk about a paper which is based on joint work with my amazing collaborators, Yamini and Boaz. And the title of the talk is Understanding Generalization Requires Rethinking Deep Learning. And I know it's a bit provocative, but I hope you understand soon what I mean. I'm going to introduce some theory and experiment that we did. So our setting is supervised learning. Here you have this black box, which is called a training procedure or a training algorithm, which gets this list of labeled data. Oh, I should mention that feel free to ask questions. I would love to have an interactive talk. So if you don't understand something, that's probably a good time to ask a question. So because I think everyone should understand what's going on in this talk. So we're getting this list of labeled samples, and we output a classifier. And our goal is to have a classifier that is able to get the right labels for unseen data. So more formally, we get a sample of x's and y's, which we call the vector of x's and the vector of y's, and we train a classifier. We call it like a training procedure, and we get a mapping from the x to the y, from the data to the labels, and we want it to have like a good performance on unseen examples. So we're going to concern ourselves with two main quantities, which is the train accuracy. This is the probability of getting the right label for a training sample. Here the probability is over the sample, the randomness of the algorithm, and the index inside the train set. And the test accuracy is the second quantity of interest, and this is the probability of getting the right label for an unseen sample. Here the randomness is over, again, the data that we saw, the randomness in the training procedure, and the randomness of the new unseen point. And the difference between those two quantities is called the generalization gap. Feel free to ask questions if this is unclear. So let's draw this for a second. So if we have this axis of accuracy, and we put training accuracy here and test accuracy here, the generalization gap is going to be this difference. And the classical learning theory kind of concerns itself with what happens when we increase the number of samples. And what we would hope is when the number of samples is large enough, we want the train and test to be close. So we want the generalization gap to be zero. And basically what we actually want is it to be pretty small for realistic sets of parameters. So even for like a real algorithms, we want to have train close to test. So, and this is a general question in statistics. What does so we have this like empirical quantity here, and we have this population quantity here, and we want to ask ourselves, what does the empirical quantity tell us about the population? So how do we usually do this supervised learning? We have this data, and we can think about training a neural network as fitting this very complex curve. And when I say complex, I mean it has a lot of parameters. So many parameters. And what we want is to separate the examples using this curve. So on one side of the curve, you have dogs, and on the other, you have cats. And these neural networks achieve pretty good performance on these tasks. So, and one thing to notice is that, like, with every year, the research community introduces new architectures that just like become more and more complex and get better and better results. And also something interesting that happens is that the train is basically 100%. So we are able to fit the train set completely. And we call those classifiers that feed the train completely interpolating classifiers. So if I say at some point interpolating classifiers, I mean classifiers that have 100 train accuracy. And in 2017, Zhang and his collaborators
Gal, you were stopped for some reason. Only me can see, Gal, or it's everyone?
Oh,
we can see. Everyone can see.
Yeah, it just froze.
Yeah, there was like some latency. I don't know what happened.
Okay,
can you hear me?
Yeah.
So what Zhang et al. Did is they used this like same data set, CIFAR10, and they took for each image, they basically gave completely random labels. So there is basically no signal in the data. And there are many interesting aspects to their paper, and I highly recommend reading it. But one interesting thing is that the train performance, it's still 100%. And like unsurprisingly, the test performance is chance. So you have 10 classes, so 10% is just chance performance. And but the fact that you still get 100% train performance, it means that the train is completely uninformative of the test. So you can have 100% train and be perfect and be like 92% on the test, and you can have 100% on the train and you can be basically, not only you're not vanishing, not only your generalization gap is not vanishing, it's basically the largest it can possibly get. And the interesting thing is basically like, if you look at each of the experiments, they're kind of not like, maybe not surprising individually, but what's surprising is they're compatible with each other. Basically, that you're like both able to generalize while you kind of behave like a lookup table, right? And so basically the bottom line from this paper is that supervised deep learning, it works great, but the train accuracy tells us nothing about test performance. And this is why they call the paper understanding deep learning requires rethinking generalization. So generalization is not a tool that can explain deep learning. And what we do in this paper is we look at neural networks that are trained in a very specific way, which I'll talk about later. And this way, we call it the self-supervised plus simple, or SSS classifiers. And practitioners known that they worked great for a long time. And now they're getting basically a lot of popularity because they're basically competitive with state-of-the-art results with standard methods. So they achieve the same results, or sometimes even better. And what we observed in our work is that they have provably small generalization gaps. So if you look at the generalization gap, it's actually small in practice, and you can actually prove it under certain assumptions. And this is basically why we call this I call this talk. It's not the name of the paper; it's just the name of the talk. Understanding generalization might require rethinking deep learning. And I should mention that there are some other works that analyze specific cases of SSS algorithms under some statistical assumptions and like specific SSS algorithms, but I'm not gonna get into details. You're welcome to check the references. So, by the way, any questions so far? Okay, cool. Okay, so what's the idea behind the self-supervised plus simple algorithms? The main idea is to try to imitate how humans learn. So, like as a human, as a baby, you don't get a billion of images of cats and being like, this is a cat, this is a cat, this is a cat, this is a cat, right? That's not how we learn. What we do is we actually get a bunch of unlabeled data, right? And we kind of like store them in some way and get something that I'll say informally, a useful representation. And we can say that it was forged by evolution, this useful representation. And then when I get an image of a cat with a label, so someone tells me, hey, this is a dog, I can understand that everything that's kind of related to a cat is a cat, and everything that's related to a dog is a dog. And the baby understands this concept, and even when I give the baby something completely different, like basically something that like a neural network or any learning algorithm would struggle deeply to understand that this and the two things are the same, but babies have no problems with that. So what those self-supervised learning plus simple algorithms do, they take unlabeled images and they use basically the same neural networks that we had before, a very complex classifier to get a representation. So the representation is going to be some function that maps an image to a vector, okay? So we get a very complex representation, and there are various techniques to get it. I'll elaborate a little bit later. And after that, we hope that this representation is going to be useful. So one example of useful means that our data in the representation space would be linearly separable. And so on top of that representation, I can fit a simple classifier. For example, a linear classifier. So two stages. The first stage is unlabeled data, where I fit a complex neural network doing some pretext tasks, which I'll elaborate in a bit. And then I'm fitting a very simple classifier on top with the labels. So first part unlabeled, second part is labeled. A little bit more formally, we can break our T of the training procedure into two parts. The first part gets the training sample without the labels and outputs a representation, which is a function from the data domain to the representation domain. And then we do a T-fit, which is going to be a simple classifier, which gets the vectors of the representation vectors with labels and outputs a classifier G, which is simple from the representation space to Y. So our final function is going to be f of x is going to be a G of R of x. Okay. And in this paper, one important thing that we do, we basically look at this whole thing as one training procedure. So we reuse the same data. So we use the same data to train R and to train G. Okay. Any questions so far? feel free to ask in Hebrew if that helps you. Okay, good. I'll assume I'm clear. So if you look at the performance of those SSS algorithms, recently they got so using this data reuse. So I'm not using any additional unlabeled data, which I could a priori, but I'm not using any additional data, and the performance of those methods actually pretty close to state of the art, if not state of the art. So there's basically like 1% difference in CIFAR and ImageNet on the classical standard benchmarks in image. And for NLP, it's basically achieves the state of the art. Okay. So one thing to look for, to notice is that the train accuracy is actually not 100%. So we already see that something interesting is happening here. So in our paper, we also replicate the Zhang et al. Paper, and the test accuracy is 10%. It's just chance. As I said, you don't get any signal, so it's not surprising. But the interesting part is that the train accuracy is not 100%. It's pretty close to the test accuracy. So the train actually gives you an interesting signal about the test. And it basically, we trained a bunch of models and a bunch of methods for this, for both CIFAR10 and ImageNet, and it's consistent. You get like a small generalization gap for SSS algorithms. So we try to kind of interpolate the two cases with full noise and no noise at all. So here you see the blue points is train, the purple points is test. And this is going to be fully supervision or end-to-end supervised. Those are going to be end-to-end. Those are going to be SSS algorithms. And as you can see, the test is pretty much the same, right? But the generalization gap is actually much, much smaller for SSS algorithms. So I'll just say like what I'm going to talk about in the rest of the talk. So first thing that we do is we break down the generalization gap into three quantities: the robustness gap, the rationality gap, and the memorization gap. We call this this whole thing the RRM bound. Then we show that in practice, the robustness and rationality are very close to zero for both end-to-end and SSS algorithms. Oh, I should mention that this RRM bound, it works for any algorithms. It works for both SSS and end-to-end methods. Same goes for rationality and robustness being small. And we also prove that for SSS algorithms, the memorization is this function of the complexity of the simple classifier. So if you remember the classifier G, if it's linear, it's just the complexity of the linear classifier. So the memorization gap is not going to depend on the complex representation. It's going to basically decay very quickly because the classifier on top is simple. And we show finally that in practice, this complexity is quite small, so it can actually give us meaningful generalization bounds for those SSS classifiers. So we get non-vacuous generalization bounds, and it might sound non-vacuous might sound like a low bar, but actually it's proved pretty hard to prove generalization bounds that are not vacuous for deep learning. So the theory of deep learning community has tried pretty hard to find the settings where we have non-vacuous bounds, and it's pretty sparse. Let's say it like that. So let's first start with the RRM bound. So again, we have this data. Notice that I don't have t-pre and t-fit. I only have this full training algorithm, and I output a classifier. And my generalization is, again, train minus test. Now what I'm going to do, I'm going to do a hypothetical mental experiment, which later will become an empirical experiment. But right now, let's call it a mental experiment. I'm basically going to fit the same data with 5% label noise to T. So I'm going to have two parallel experiments, one where I fit data and regular labels, and one where I fit 5% noisy labels. So I introduce 5% of the labels are completely uniformly at random. Okay, so 95% I get the same label, and uniformly at random I get a wrong label with 5%. Okay, and let me call F tilde the classifier output by the noisy experiment. And sorry for the tilde, I don't know what happened to it, but believe me, it's a tilde. Okay, so again, I'm feeding this data, and some of the data, basically this dog, as you can see, it's actually, I'm giving the classifier a label of a cat. Okay. So the robustness gap is going to be the performance on the train. This is going to be train accuracy minus the train accuracy of the noise classifier, okay, when measuring against the original labels. So I have two classifiers, and I measure them against the original labels, and the only difference is one was produced when I introduce some label noise. Okay. So for interpolating classifiers, and I'll remind you that interpolating classifiers are classifiers that get 100% train accuracy. This thing is going to be 100%, right? The accuracy on by definition is going to be 100%, and this thing is also going to be 100%, but on the noisy data. So on the original data, it will get 95%. Okay, let me know if this is unclear. I'm just giving an example here. And so my robustness gap in that case is going to be 5%. Okay. And
can I ask a question? Why is the second classifier gonna get 95% on the test? Because maybe you're just overfitting the noisy examples, but you're still fine on the distribution.
So it's only the robustness gap only concerns itself with the train. It's only on the train. I'm not talking about the test at all.
Okay.
Okay. Thanks. So maybe I'll repeat like this example again. This is going to be my performance, my regular train performance. Okay. And this is going to be my train performance of the noise classifier. Okay. So it's basically I'm measuring the same thing for two different functions. And the question is how much the performance on the train set degrades when I get noise. And for interpolating classifiers is going to be at most 5%. And intuitively for methods that are simpler, you're going to get even less. Okay. Okay. So this quantity, I'll call it noisy train accuracy, and this is going to be a robustness gap. Next, we have the memorization gap. Okay. So this
Can you
quantity
explain the motivation for calling it robustness gap. So why do you treat it as being robust?
Sure, it's basically robustness under. So robustness is a very overloaded term in machine learning. Unfortunately, you have like adversarial robustness and you have out of distribution robustness. But basically, what we want to say is your performance doesn't degrade much. You're robust to noise. Okay, so you could call it also noise tolerance. There are like different names or stability, but they're all overloaded. There is no escape. So like if you didn't like robustness, wait for the rationality. That's the actually controversial one. So we have the memorization gap, which is the performance, like the performance of the noisy classifier on the train minus the performance of the noisy classifier on the train conditioned on a wrong label. So I have like a bunch of right labels, and then I have a wrong label, and I only ask how do I perform on the wrong labels. Okay. Intuitively, this is the ability to memorize the wrong label. Okay. And finally, is the memorization gap clear? So here, when I condition, I'm only asking how do I perform on wrong labels. So here is how I perform in general with the noise degraded classifier, and this is how I perform on the wrong label. So this the difference is actually memorizes my ability to memorize the wrong label. Okay. Feel free to ask questions. Okay.
So can you go back to the formula? So yes. Shouldn't it be like f tilde of xi being equal to y tilde I? So like if you want to measure like your ability to memorize wrong labels, then like you should see the probability of
yeah, I think it's a good question. Basically, you're going to measure very similar things. This is kind of the quantity that we need to break down the generalization gap into 3 quantities. So the intuition for both of like what you defined and what we define is basically the same thing. It's very like there is a one-to-one function from one to another, right?
Yeah.
So can I ask a question? Sorry.
Yeah, sure.
Continue after him.
What?
You didn't finish your answer. Sorry.
Oh, so I think I actually did.
Okay. So I have a small question about this memorization gap formula.
Sure.
Can you explain why it's always positive? I mean, why it is always the case that the left-hand side is greater or equal than the right-hand side?
So first of all, I didn't say it's always positive. It could be negative.
Okay, but it was implied because you you put the red dot in the left side of the green dot.
That's fair enough. But usually your performance on wrong labels, I mean, it can be negative, but I think it's very rare for you to be more correct on right labels than wrong ones, right? Especially on the train. So I give you like I give you an image of a dog and tell you it's a dog. I give you an image of a dog and tell you it's a cat. And so it will your performance on the dog would be better than your performance on the catted dog.
Yeah, okay. Of course I agree, but yeah, we'll talk about it later. Okay, thanks.
Yeah, thanks for the question. Other questions about the memorization gap? I mean, in the end, it's just a quantity that we defined, and that's the intuition behind it. It's the ability to memorize the wrong label, and I think it's a pretty precise intuition. So it can be wrong, but like it can be negative. Sorry, but it usually won't be. That's kind of my full answer. Okay, and now we have the rationality gap. Okay, And I know rationality is a bit provocative, but I hope that I'll be able to convey why we called it the rationality gap. And this is the performance of this noisy train accuracy on noisy samples minus the test performance. So basically, it's the performance on unknown labels, the test examples, versus performance on wrong labels. Okay, and as Alon mentioned, a memorization gap can be negative, but the rationality gap will definitely be negative for interpolating classifiers. So for interpolating classifiers, this thing is going to be so on wrong labels, you're gonna be basically always wrong, right? Because you feed the data too well. So this quantity is going to be very negative, actually. So I'll just give one example because the rationality gap can be quite confusing. So by the way, we call it the rationality gap because it's kind of, you should perform better, like wrong information should be only worse than no information, right? This is kind of the idea behind it. But you could actually like look at this example. So assume we have test accuracy 70%. We have a classifier that is correct on 70% of the test, 70% of the test distribution, okay? And assume that we have a rationality gap, which is 10%. So basically, if the rationality gap is positive, I call the classifier irrational, okay? And why do I call the classifier irrational in this case? It's so again, I get this sample where these are like correct things, and I get this dog, which is the classifier thinks that, or the input for the classifier is a label cat, okay? And so this is not a cat, but the classifier thinks that it's a, or at least input that it's a cat, okay? So now I get an unseen sample, which is this dog, okay? My probability of getting it correct is 70%, okay? But the probability that this thing is a dog is 80%, because that's just reinterpreting the rationality gap, okay? So if I just add the rationality gap to the test, that's what I get, okay? Because that's my performance on unseen samples, okay? So what I could do is, instead of like doing this, right? Instead of just doing inference on this dog, which I haven't seen with no label, what I could do is just put it in the train set with a random label, and then I get here, right? This is basically a reason for the rationality name. Okay, so I can take the dog with no label from the test, and I can retrain the classifier with a new with this new dog inside with a random label, and then I get, instead of 70%, 80%. Okay, so I can actually improve test performance by retraining with a random label. Okay.
Assuming you're knowing which one is the random label.
So so this dog, it's a test example. Okay, so I have no label for it. So one thing I could do is just take my classifier that the T gave me, that the training procedure gave me, and do inference. Okay, I do inference, I get 70% to get the dog. Alternatively, I defined a T prime, which instead of doing inference on this dog, I'm actually retraining the whole thing with a random label for this dog. So instead of doing inference, I'm doing retraining with a random label. And then, since my rationality plus test is going to be, it's going to be basically test plus rationality gap, is going to be this thing. So you actually get 80% performance. I know it's a bit confusing, so feel free to ask questions. And basically, we get this performance on the table theorem that I explained in words, that you can trade off a rationality gap for test performance at the cost of doing inference at the time that is basically your training time. So you don't actually want to do it. It's not an advice for practitioners. If you see a rationality gap which is high in your algorithm, it doesn't mean that you should start like putting random samples with a random label inside your train set, because the inference would be much longer. Okay. But it is a sign that something irrational is happening. And like I believe that deep learning practitioners are pretty good at what they do. So the rationality gap is actually going to be pretty small, because if you could, you would reduce it. Cool. So we have this RRM bound, okay? And why is this a bound? Because we actually defined, sorry, iPad. We defined the bound to be something like that. So instead of robustness, we have maximum of 0 and robustness, and rationality is maximum of 0 and rationality. So this is actually becomes a bound. It's not much of a theorem. It's more of an observation, but we believe it's a useful one. What happened? Okay. Good. Okay, so we have this RRM bound, and now we're going to talk about the specific quantities in this bound. Any questions about the RRM bound so far? Okay. So let's look at a bunch of experiments we did with many SSS methods with all kinds of different architectures and the SSS training algorithms, and we compare them to similar architectures with end-to-end supervised methods, okay? And as I mentioned, for SSS methods, the robustness gap is going to be 5%, but for fully supervised methods, the robustness is going to be 5%, but for SSS methods, the robustness is kind of smaller, and the rationality for fully supervised methods is very negative, but for SSS methods, by the way, I should mention the experiments are on CIFAR. We also have experiments on ImageNet, basically the same results. And we see that the rationality gap is pretty small. So if you look at how irrational, so irrational is this axis, how irrational classifiers are, they're very, very irrational. Basically, it's negligible. And now, when we look at memorization, we see that it forms the lion's share of the generalization gap, okay? That for supervised methods, the memorization is very, very high. And for SSS, it also can get pretty substantial. It's almost all of the generalization gap is the memorization gap. So to summarize, robustness and rationality are small for both the supervised and the SSS algorithms. And the memorization is large for supervised and small for SSS. And there are also like some proofs in the literature that the robustness gap should be small. They don't cover like the full range of what we expected when we start doing the literature review, but there are actually some proofs that show that the robustness gap should be small. Rationality is a completely new quantity, so there is not much to say about it, but the memorization gap, we actually prove that it's small for SSS methods. So our theorem is that for SSS algorithms, when they learn the representation R and fit a simple classifier on top, basically memorization is bounded by the complexity of G, which is the whole point. And notice that the data reuse is an important an important point here, because if we don't reuse the data, if we have completely independent data, then it's clear that it's just concentration bounds. There is like nothing special here. But when we do data reuse and the memorization gap is small, and we assume that the rationalities and the robustness are small, then you actually get a proper generalization gap bound. Oh, yes.
Can I ask a question?
Sure.
So n here would be the number of samples. But this is the unlabeled or labeled samples, or you're not separating?
I'm not separating. Yeah, it's just the number of trained samples. If you
So
have
you're
some
not assuming that. So it's not the setting where I'm training on, I don't know, only 1% of the images in ImageNet or something.
No, in a sense, what we assume is the worst case, which is full data reuse. If you have 1% of the labels, then it's only better. So if you don't have any data reuse, you get like trivial concentration bounds. There is like nothing to talk about. Your generalization gap is going to be basically zero. But we're assuming the worst case.
But if n here is very small, then I'm still suffering from the memorization gap, right? Which
Yes.
would be the case if I'm using only a small subset of the labels.
No, wait, but I think you would have some. I think I need to think about it, but I think you'll have to. You'll basically have some averaging between the the case where you have. Okay, yeah, I agree with you that if you have a very small number of labeled data, you can be hurt. Yeah, I agree. But yeah, I'll have to think about it. Like we can talk about it later.
Okay, sure.
But yeah, it's a good question. Basically, I think it should be fine, but I'll have to think about it a little. Any other questions?
Yeah. How does this depend on the representation? I mean, you can have just garbage representation.
Yeah, exactly. So basically, if your representation is completely garbage, your train would also probably going to be garbage. So, and then you don't get anything interesting or meaningful. So
okay, so what do you mean by complexity here?
So if you think about a linear classifier, I'll go into details in a second, but like think about maybe the number of parameters or something like that.
Okay.
And so what you assume in the representation you get from a practitioner is pretty good, because he uses it, and so the fact that the representation is good and the generalization gap is small gets you a good performance.
Okay.
So if your train is good, your test is going to be good.
Okay.
This is kind of what it means. Any other questions? Okay. So we have this. I'll go briefly over the proof of the theorem. So we have this whole mechanism, the SSS mechanism to feed the data, and we let G to be the output of the fitting procedure, and we want to bound this memorization gap by the square root, something that grows as a square root of the entropy of G over N. Okay, and this is bounded, for example, by the number of bits taken to describe G. Okay, and so we define two random variables, A and B. A is just going to be whether the prediction is correct, and B is just going to be whether we incurred label noise. Okay, and it suffices to show that the mutual information between A and B is bounded by the entropy of G over N. Why? Because basically this thing is just E of A, and this is E of A given B equals 1. Okay, and there is a famous inequality called the Pinsker inequality, which with a small amount of massaging gives you a bound of this memorization gap using the mutual information between A and B. How do you show this thing? It's not that complicated. You write the formula for mutual information as the difference of entropies between HB and HB given A. This is smaller than this conditioning on the index of HB minus the conditioning of HB given A. Why is it smaller? This is just the index is independent of the noise. So this is actually equals, this and this are equal. And here we use the fact that the entropy always reduces, conditioning always reduces entropy. And let me know if I'm going too quickly. So this is just the mutual information conditional on the index. And since G stores all the information needed for knowing whether a prediction is correct, the mutual information of G always larger than the mutual information with A. And this is just a fact from information theory, a short proof, a short lemma from information theory. And finally, we just bound the mutual information using the entropy of G. It's once you have the definition set, basically the proof kind of proves itself. So high level, what I did is I basically showed that the correlation between a wrong prediction and a wrong label is small. And if G is simple. So if your classifier is simple, it kind of doesn't care where the predictions were wrong. If the classifier is complex, then it will memorize basically. And if not, it kind of will get like be wrong whenever, independently of where the labels were wrong. Okay. Any questions about the proof? Okay, good. Cool. So we proved that, and now we just show that in practice this complexity is small. Basically, showing what's the entropy of G, it's kind of hard. So we use something more close to this mutual information instead as a computable bound, and we showed that we basically add the robustness and rationality to get us like a theorem, like a generalization bound. Sorry. So let me plot this series of classifier, and I sort them by their generalization gap. And this is going to be just the generalization gap. So this is the y equals x line. Okay. And every vertical line is going to be a classifier. Okay. So first, I plot the memorization gap, which, as you can see, takes a pretty large chunk of. So each line is a memorization gap of one architecture and one SSS algorithm. So this is the memorization gap. This is the rationality gap. You can almost not see it. It's so small. And on top, you have the robustness gap. Altogether, when you sum all three of them, you get the RRM bound. Okay, as you can see, it's always above the generalization gap. And on top, we just show our proven bound. Okay, and as you can see, it kind of correlates with the memorization gap. And if you squint really hard, it also correlates with the generalization gap. Any questions about this plot?
Your bound is only on the memorization, right? The rationality and the robustness are assumed to be empirical or zero.
Yeah, exactly.
Okay.
Yeah. So like if you want, like, add 5%, like assume that the robustness and the rationality are below 5%, and then you get a bound. At least that's how I look at it. Okay, so to summarize, we have SSS algorithms, which as practitioners know for a while, they're great in practice, but they actually work in some sense in theory too. And to touch upon a little bit on open questions, so we have like basically robustness and rationality bounds for specific algorithms. So we kind of didn't assume anything on the algorithm that you do SSS with. So you could say, well, look at this Sinclair algorithm, which is great. We can actually prove that its rationality is small or something like that. And also, I think more high level is how would you formally define what's a good representation? I think that's a question that still remains, and one of the most important and interesting questions right now in representation learning theory. And another question that you could ask is, like, what happens when you do full end-to-end supervised training, and do you implicitly do some kind of representation learning, and can you use our framework to say something interesting about end-to-end training? And yeah, that's basically it. I take any questions now.
I wanted to ask, so you showed how your framework, the SSS framework, you have a pretty good explanation of how it generalizes, but then it brings the question, does it help to shed light on how like regular end-to-end supervised learning algorithms generalize? Like, do you think that something similar might be going on in regular deep neural networks, that it's somehow they do some representation and on top of that some kind of simple fitting?
I can only speculate. So I think that this SSS algorithms at this point, they basically do something very close to just smoothing out end-to-end methods. So that's why you don't fit all the points. But I mean, it's a very important question, a very interesting one, and I don't like. I think it's worth studying and working on.
I'd like to ask a question.
Yeah, sure.
Yeah, so actually, going back to that last point, I don't remember who it is with. It seems like regular neural nets, regular supervised learning, is capable of doing this. The problem is that the regular end-to-end neural networks are too powerful in a way.
Yes.
They're able to overfit or something like that. So is there a way of just, it seems like what you're doing is limiting the complexity of the model in a way, and maybe adding some regularization term to the loss or to something would maybe achieve the same goal?
I mean, it's possible. it's kind of like hard to imagine adding a regularization term that it kind of acts gets you this like very different representation than you're used to. Like basically, usually in end-to-end methods, regularization only hurts you, right? They almost don't do any regularization or do a very tiny bit of regularization, and what they do instead is just increase their methods, right? So you just like, if you look at the progression over time of neural networks, they get just like larger and larger and larger, which is a priori the opposite of regularization, right?
Yeah.
So I don't know. It's a good question. It's possible, but I don't know.
Or you know, I'm not an expert. Like I'm right now taking my first course in neural networks, but from what I've heard, there's also something called dropout. You can, you know, randomly drop out or not use some of the neurons in the net, and that also limits the overfitting. So I don't know, is that another thing that could be tried, or does that do the same thing as your method? Or
so all kind of regularization methods that people actually use in practice, they either hurt the test performance substantially, or you still get like 100% even on randomly labeled data. So the Zhang et al. Paper, they actually do experiments with all kinds of regularizations, and they still get 100%, like standard regularization, and they still get 100% or 99.7% on the train, even on randomly labeled train. But again, I'm not saying it's impossible to have like this perfect regularization, and I know a lot of people are trying to find this perfect regularization that would get you to a great performance on and no overfitting, but so far no one was able to.
Great, thank you.
Thanks for the question.
Yeah, I have a question.
Mm-hmm.
Assuming the simple classifier at the end to be a linear separator.
Yeah.
So the difference between a neural net and the SSS algorithm is decoupling the representation from the separation?
Yes.
Okay.
Exactly. It could also be like maybe a two-layer or like highly regularized classifier, or like maybe sparse regression. But yeah, in that case, yeah.
Okay, thanks.
I have a technical question.
Sure.
When you divided the learning to two parts, right, the representation and the classification, do you update the parameters of the representation also? Like,
oh, okay. Yeah, so that's a good question. I also forgot to mention how people do representation learning, so I can also touch briefly on that if you guys want. But there is also two kind of ways to fit to do the final fit after the representation learning. You either just train a classifier on top and don't update the representation, or you do what people usually call fine-tuning, where you update the whole network. So what we do is we only do a simple classifier on top, but the practitioners actually squeeze like 1% more performance by fine-tuning. And like you can perhaps do a similar analysis to what we do if you don't change the representation too much. So if you have like small number of steps, you basically don't, you're gonna get like stability guarantees on the representation.
Okay, thank you.
So just like, because I forgot to mention it, like how people do train this representation neural networks, what they do is they usually, like right now, there are many ways to do it, but right now the most popular one is contrastive learning. When you take an image, you create like a couple of augmentations of the image, and then when you have two augmentations of the same image, there's the same label. And when you have two augmentations of different images, they're different labels.
So you have as many labels as you have data points?
Yes. There is actually like one method called instance discrimination, where the label is actually the index. So the index, like, so let's say you have a cat numbered 1137. That's actually the index that you train the network with. And then you discard the last layer and train something on top. And there are also other popular methods. So you have like completion. So for example, that's not contrastive learning. So you have like half the image and you try to predict the other half. Or you have a kind of some kind of a jigsaw puzzle and you try to complete the puzzle or something like that. And there is also methods based on generative methods, all kind of GANs and autoencoders that you can take internal representations. But right now the most popular one, at least for images, is contrastive learning.
Okay, so again, thank you, Gal, for this great talk. And if you have any further questions, then I think you can approach Gal and ask him. And thank you again, and for everyone for coming. So
thanks.
See you next week.